Okay, so I think we can move forward, and I'll keep adding people as they keep coming in, but we'll see. Okay, so let's just start. So thank you all for coming. So this will be our third session in machine learning using Python, and today we'll be going over the generative adversarial networks. These are really interesting. They have a ton of applications, but they can also get really involving in terms of the math and the programming behind that. So these are not the typical introductory machine learning models. These are pretty advanced, which came out after like 50 or something years of research. And the first paper on GANs was only published like in 2014. And we'll be getting into all of those things, but some information before that. So unlike the other sessions, in this session, I'll be the only host. Alric will not be there. So it might be harder for me to interact, but it doesn't matter. If you guys have any questions, just feel free to unmute yourself or type something in the chat, and I'll try to answer them as quickly as possible. So, okay, let's just get started. Okay, so before we move forward, here is the broad outline of what we'll be doing today. I'll begin by showing some motivations to learn GANs and move to present a brief review of the widely used GANs-based applications. Then we will see what generative models are. And so since GANs is basically generative adversarial networks, we'll try to see what essentially constitutes for the generative part of the model. And then we'll look at the structure of the GAN. It's made up of a generator, a discriminator, and things like that. We'll be looking at how to train these different parts of a GAN. And finally, as always, we'll also look into a bunch of mechanical engineering applications that use GANs. And finally, we'll have a small programming session where we'll program our own GAN from scratch. So that should be really interesting. I hope you guys all have the Collab notebooks loaded up and ready to go. And okay, so GANs were proposed by Ian Goodfellow et al. In 2014, like 6 years ago. And this is one of the most cited works in computer science. This is like a really small 7-page paper, and this has been cited like 30,000 times. And interestingly, this is a part of Ian Goodfellow's PhD thesis research at the University of Montreal. So he was still a grad student when he proposed this. And so what do GANs do essentially? At the core, they are trying to learn the probability distribution of the samples that are fed into the model. So if you are feeding images, then it is trying to learn the image distribution. So the idea is that once you learn the distribution, you can choose other points that make up the distribution. So if you are training a GAN using images, you can essentially produce images that belong to the same distribution, but which have never existed before. So as seen in this image, the faces are all generated using GANs and do not correspond to any living person. So if we look at the progression, the first face was generated by Goodfellow et al. in like 2014, and this barely passes as a realistic face. But in just 4 or 5 years, we were able to produce basically images which are undistinguishable to the human eye. Uh, the last one is produced by using something called as a style-based generator architecture for GANs that came out in late December. And I have also provided the archive link on the top for this style-based GANs, which is one of the most advanced GANs if anyone is interested to pursue further. And you can do a lot of interesting things using GANs. One of the common things is probably interpolating between different samples which you are feeding into the GAN model. So I bet you must have seen something like this, which looks really cool. And here they are basically decomposing the facial features into three different types. So you have coarse styles and middle styles and fine styles. These are basically the frequency decompositions of the image, and you're saying like retain the features which you have in the middle and the fine style images, and basically start changing the core style images, and you are saying, okay, give me the interpolation between these three faces. So as you are changing one part of the feature, you can literally see them morph from one face to the other. This can be intuitively understood as points closer to one another have lesser difference between them, so they are less distinguishable for the human eye. So it looks like the faces are literally morphing from one face to the other. You could also use image interpolation between static images and actual video footage. So if you take a static image of, say, Mona Lisa, and you feed in a video footage of someone else who is either talking or smiling, and you try to do an interpolation, it looks as if Mona Lisa is doing all these things and she's talking or moving, and this is really interesting. And other than the ones which we have seen so far, there are like a ton of applications using GANs. These are a bunch of advances which are made using GANs, and this is just a brief review. The idea is to make you guys familiar with the common applications which are used with GANs, and maybe somehow modify them and integrate them into your own research. So notably, the essence of GANs is generating the distribution of samples. That's it. So if you start feeding in samples, GANs essentially learn the distribution of the samples. So for example, if you start feeding in points of a normal distribution between, say, -1 and 1, GANs essentially learn the bell curve. So analogously, if you keep training them using images, they'll start learning the two-dimensional or three-dimensional distribution if it's an RGB image. So the other example is, once you learn the distribution, you can have new samples from the distribution which were not a part of your training data. So this feature is used to generate like realistic artificial faces, which we have seen so far. And another really crucial application of using GANs is time series prediction and future simulations. These are useful for in the fintech sector. They are used for predicting stock market values or things like that. But for us mechanical engineering researchers, these are really useful if you are trying to simulate the future values of state variables for dynamical systems. Notably, they are really useful for fluid simulations. And they are also useful for filling in missing values. So what do I mean by that? So one aspect of this could be image interpolation, so filling in missing values between two different samples. The other one could be um, okay, wait a second, I think I have a question. Oh yeah, totally. GANs will be able to identify specific distributions. So in the programming session which we have, we are actually trying to do the same thing. We are trying to learn using one-dimensional data if we can learn a one-dimensional normal distribution. So just hold on to it for a minute. We'll actually program something and see how well GANs perform. So that'll be really cool to look at. Okay, so going back, filling in missing values. This is either filling in missing values between two different frames, or actually filling in missing values in a certain simulation. So these could be reconstructing corrupted simulations or interpolating to smoothen out the simulation or things like that. Notably, GANs have significant influences in semi-supervised learning, where you have a ton of data and this is not labeled. So you have partial labels for your data and you want to train your model, then GANs become very useful. So these are like the sweet spot between the supervised learning and unsupervised learning, where you can use partially labeled data and still form conclusions which are not totally supervised. Then we have text to image sequences. This is like a really cool consequence, but I don't think we'll be using it in mechanical engineering. So this is it literally sounds like magic. Like you basically write a sentence and the GAN would give you an image of the description. So you could have an image which, so if you were to write like a cat playing a piano on a ship or something like that, a GAN would generate an artificial image which matches all these descriptions, and this could be something which has never existed before. So that's pretty cool. And image inpainting is basically reconstructing slightly corrupted simulations. And finally, super resolution is my own field of research. Uh, in super resolution, you basically begin with low resolution simulations and then upscale them to higher resolution simulations using GANs. So since GANs are feed-forward models, using GANs is essentially almost instantaneous. So you begin with simulating low resolution simulations, which can be really computationally inexpensive. And you use a simple GAN and instantaneously improve the resolution of your simulations. So that's pretty interesting. And it's one of the leading applications of GANs in mechanical engineering or fluids research. So next, let's actually understand what are generative models. In order to understand this, let's try to recall the kinds of models which we have been learning so far. Um, so we did a session on artificial neural networks and we did a session on convolutional neural networks, right? So these are both discriminative networks. So what do I mean by, so what are the differences between a generative model and a discriminative model? Let's formally define them. Like a discriminative model directly estimates the posterior probabilities. So this could mean just simply doing logistic regression or artificial neural networks, convolutional neural networks, support vector machines, or nearest neighbor algorithms. So these are all falling under the category of discriminative models. And whereas generative models, instead of simply learning the posterior probabilities, since posterior probability is simply the value of a variable, so this could be a conditional probability, or this is basically a value. But on the other hand, the generative models essentially learn the model class conditional PDF or and the prior probability. So once you have the conditional PDF and prior probabilities, you can essentially uh, know the distribution of the variables which you are dealing with. So an example of generative model would be generative adversarial networks or Gaussian mixture models and Bayesian neural networks. So we'll be looking into GANs more in detail, but just to give a glimpse on the other kinds of models, Gaussian mixture models are really useful if you are doing Bayesian optimization, or if you are trying to untangle a PDF, which is a mixture of two different types of Gaussians. So that's really important if you are doing something like MCMC or uh, Bayesian optimization for hyperparameter tuning or things like that. And even if you are training Bayesian neural networks, Gaussian mixture models could be really useful. So I know though those examples, like these definitions, were probably very they are not really intuitive if you are not familiar with probability theory and statistics. So I want to give an intuitive example of the differences between the generative approach and a discriminative approach of learning models. So say you want to train a model to look at a speech and identify its language. So we want to identify the language in which the speaker is giving the speech. So in a generative approach, we try to learn all the languages and determine which language the speech belongs to. And in a discriminative approach, instead of learning the language, we are only learning the linguistic differences to make a prediction as to which language the speech might belong to. So in general, if you think about it, right, like learning all the languages corresponding to the speech and trying to distinguish something is a really tough job. As an example, if you want to check if a speech is in French or in English, it is extremely hard to learn both French and English perfectly and then make a guess, compared to simply learning the differences between what French and English sound like. Like the French, they put more stress on certain sounds like their R's, which are easy to identify in a speech. So it is really easy to simply identify the differences than actually learning the entire language. So this can be used as an intuitive thought experiment to understand why it is so much more hard to understand, to train generative models than discriminative models. So because of those differences, we have a slightly complicated looking structure for a GAN. Compared to the ANNs or CNNs, this has more moving parts, but the fundamental principle is very simple. For now, I want you guys to focus on the workflow and particularly uh, on the red and the blue blocks. Okay, so let's go over the workflow for beginners. Like for starting, we have a set of real images, and if we have real images, we can take a sample and like a sample of the real images, and this sample is fed into the discriminator. On the other hand, we have a random input and it is fed into the generator, and this generator also produces its own version of the sample. So this generator is taking in a random input and then producing a sample. So this part is really important. So this is the part where the GAN is essentially learning the distribution. So after training, this would actually correspond to a PDF or a distribution. So the discriminator, right? The discriminator takes in samples both from real images, like the trainable training data, and it also takes in information from the generator. So this is, we can call it synthetic or fake data. Okay. Oh yes, both G and D are neural networks. Totally. They could be convolutional neural networks or fully connected networks. So that's the essence of it. We get to build over like what we've been learning so far. So so the generator also produces a fake or synthetic sample, and there is a real sample. And the job of the discriminator is to basically distinguish between both of them. So it looks at the real sample and it tries to learn what a real sample is, and it looks at the fake samples and it tries to detect that it's a fake. And the output of so the discriminator is basically a binary classifier, right? It can either classify something as fake or something as real. So this is basically a binary classifier, and it has two outputs for each class. Classes being fake or real. That's it. And this is basically what's happening under the hood. And we have a data set from which we can take real examples, and we also have a generator which tries to produce fake examples with the sole intent of fooling the discriminator. And this is basically like the generator is basically a con artist, and the discriminator is basically an art connoisseur or something. So, okay, wait, we have a question. Does the random input need to be anyhow related to the real images? It totally should not be. The reason for that is we are trying to, okay, so let's intuitively try to understand the purpose of a random input, right? So we are not trying to compare uh, classes in a GAN. We are trying to only see if a sample is real or fake. So the goal of a random input is to basically say, okay, the generator is essentially learning a distribution, right? So after it learns a distribution, basically throw me a random sample from this distribution. That's it. So the random input's only purpose is to basically get a random sample from the newly trained distribution. Does that make sense? Okay. Uh, it'll make more sense when we are programming things, but I hope that was clear. And okay, so this part can essentially be understood as, okay, so the generator is actually not dependent on the real images. Okay, wait, I'm going ahead of myself. This will be more clear once we learn the loss functions which we are using to train the generator and the discriminator. Okay, so here a generator tries to produce a fake image without the knowledge of the without the knowledge of the data set, but its only goal is to um, kind of fool the discriminator. But since the discriminator has a knowledge of real examples, in a sense, generator is also aware of the kind of data the discriminator is dealing with. So this is very interrelated. So while training, discriminators' loss functions are essentially both functions of the dataset and the generator, but the generator's loss functions are only functions of the discriminator. Uh, this will be more clear in the next slide, in the next coming slides. Uh, so here is what it looks like in practice. Okay, so now that we know what's happening, like on a broader level, let's try to look at the left hand side of this model. So this is the most important part of the GAN, since this is basically where the training's happening, and this is what we'll be using for analysis in the later parts. And this is basically a static data set. Since it's real images, we are not going to modify them at all. So So the generator network is essentially taking in some noise and producing a random sample from the generator. And both the fake image and the real image are fed into the discriminator network. And it essentially says if it's real or fake. That's it. That's basically what's happening on a GAN. Um, On the top of that, we, as Leon said, like both the generator network and the discriminator networks are neural networks. Um, but here the distinction is that the generator's neural network is used to produce a sample, whereas a discriminator's network is used to produce a classification, the classification of being fake or real. So as we have seen in the last session, a popular loss function for classifying images is basically the cross entropy loss function. Since this is a binary classification, the discriminator network uses a binary loss entropy function. So let's specifically look at what the loss functions for both the generator and the discriminator look like. Okay, so this is our overall structure which I have for reference. And to begin with, let's call the random input as Z. So, or Z is the random noise, and let's call generator G. So G of Z produces a fake sample. So G takes in the random noise and it produces a fake sample. And the real images, the real data, X, let's just call it X, and the discriminator takes in a sample. So this sample could belong to either the real data or this could belong to a fake data which is generated by the generator. So let's just call either of them, let's have a variable y. So d of y essentially is the probability with which the discriminator thinks that y is real. So since we know the function of a discriminator, we know what it should do. So if the discriminator is taking in a real sample, we want the p to be high since it's real. And if it's taking a fake sample, then we want the discriminator to say that it's fake. So if it's taking like g of z, then the d of g of z should be really low, since that's not real, and this is a probability of being real. So let's see how we can write the loss functions for these networks. Since for training each network we need a loss function, right? And we have two networks. So this the generator and the discriminator are the only trainable parts of a GAN. So we need two different loss functions since their functionalities are different. Let's start by looking at the loss function for a discriminator. So, okay, so it looks really complicated, but it is essentially what we have been talking so far. There are basically two parts to the discriminator, the first term and the second term. So we have these minuses before these terms. So let's basically break down this whole equation. Every neural network tries to minimize its loss function, right? And we want to maximize the probability that a variable is real or maximize the probability that a variable is fake. So we are essentially trying to maximize something and not minimize something. So since the neural networks essentially minimize a process, we are trying to add a minus symbol and basically converting it to a maximization framework. So we want to have a normalization between the two different functions of the loss function. So we have a 1/2 in front of each term, and the big E, which is the fancy E, is essentially the expectation value. So this literally means that we are taking into account all the samples of the training data set. So that's it. So this is the expected value, and let's focus on this part. So log of d of x. So x is the real data, and d of x is basically the log of d of x is kind of the probability of x being real, and since d of x gives us the probability, so we are taking log since it's more stable in a loss function. So this term, the first term is essentially saying maximize the probability that a real data point is real. And on the other hand, this is exactly the same, but here we are taking 1 minus d of g of z. So we know g of z is a fake sample, and d of g of z is the probability with which the discriminator thinks that the fake sample is real. And 1 minus the term basically uses the probability that um, the g of z is fake. Since we are getting the output of d is the probability that something is real. So if we want to have the output of something to quantify like the proportion with which it thinks it's fake, we basically do 1 minus that, since there are only two classes. So that's the loss function for the discriminator. I know it's a lot of math, but did that like vaguely make sense of what's happening like inside a discriminator? Or would you guys want me to go into more in detail? Um, okay, so it's not actually distinguishing it from noise, since we are feeding in. Okay, so z is noise, right? But g of z is essentially a fake sample. So it's trying to distinguish between a fake sample and data, or data being real sample. So yes, I think uh, yeah, go ahead with your question, Laurel. Yep, it distinguishes between g of z and x. Nope. D of g of z is still, since the output of d is basically the probability that something is real, d of g of z is basically the probability that the discriminator thinks the fake sample is real. But we don't want that. We want that term to be really low. So we are adding like the 1 minus of d of g of z. And is the cost function like a cross entropy, since you mentioned that it's kind of like binary classification? Totally. So this is literally a variant of cross entropy. You have the probability of something being true and probability of something being fake. So it's basically like the probability of it being in class 1 and the probability of it being in class 2. And our classes are fake and real. Okay, so let's also see the loss function of. Okay, before we move ahead, like, did that make sense, Laurel? Okay. So in the loss function for generator, we are basically seeing. So generator is functioning on the other end of the spectrum, right? A discriminator, we want to say a fake is fake, but generator is trying to fight against the discriminator. It wants the discriminator to think of its fake outputs as real. So, so it is trying to maximize the opposite term. So it is basically saying like maximize the d of g of z. And so to summarize things, the discriminator is basically maximizing 1 minus d of g of z, and the generator is trying to maximize d of g of z. That's it. And the quality of a discriminator gets better since it's also being trained on a real data. Okay, so this is like this is like a summary of all the loss functions that we have. The first one is basically the GAN, which is like one of the early models of GANs which came out. So this is what we have been looking at so far. And these are a bunch of examples of the different kinds of discriminator and generator loss values which you can have to train your models. So would you want me to repeat the fundamental difference between the loss functions? Okay. Okay. So let's just call this term um, x cap, x tilde. So let's say this term is x, and this sample is. I'm writing with my mouse, so it's really bad. But okay, so this term is x. So a real sample is x, and a fake sample is x tilde. Okay, so so the discriminator, it takes in any variable, like it either takes x or it takes x tilde, and its only purpose is to say if its input is real. So it takes something, it says the probability with which it thinks that it's real. So d of x is the probability with which it thinks that x is real, and d of x tilde is the probability with which it thinks x tilde is real. But while training a discriminator, we want the d to think of x tilde as fake and x as real. So since we wanted to think x as real, we just have a log d of x. But since we wanted to think x tilde as fake, we have 1 minus d of x tilde. And that's basically the loss for discriminator. Now let's look at the loss for generator. In the generator, we want the generator to produce samples such that the discriminator thinks that they are real. So we want it to think the fake samples are real. So what is the probability of the fake sample being real? It's basically d of x tilde. So we have d of x tilde, and we are trying to maximize that. That's it. So here it is maximizing the fake samples being real, and here it is maximizing the fake samples being fake. Since this is the con artist and this is the cop who is trying to catch or something like that. So does that make sense? Like, was it like clearer than the last time? Awesome. So these are like a bunch of commonly used loss functions, which we can, or you guys should totally come up. You guys will probably come up with your own loss functions if you are building your own GANs. These can be really influential. Like sometimes you can just come up with a new loss function, and that could be the next big thing. So, okay. So let's look at the training process for a GAN. So, so this is really simple. We have two different networks, and we have a data set. So, so we begin by holding the weights in the discriminator constant, and we train the generator network. And then we hold the weights in the generator network constant, and then we train the discriminator network. So in an epoch, we are ideally updating the weights of a discriminator and also the generator. But from practical experience, it has been found that a generator is able to outperform the discriminator like way sooner. So essentially, the rate of progress between the discriminator and the generator is not on parallel to each other. And since the quality of training a generator also depends on the discriminator, we want both of them to be on par with each other. So it is a common practice while training to train the discriminator a couple of times before updating a generator. So let's say you can train a generator you can update the weights in a discriminator like 10 times and then update the generator only once or something like that. Just basically give more weightage to the discriminator while training. Okay, so now that we basically know the essential structure of a GAN and the loss functions and the training and what's happening inside, let's look at a couple of papers where GANs are used in mechanical engineering applications. So this is close to my field of research. So in this paper by Subramaniam et al., it came out a couple of months ago from the Center for Turbulence Research at Stanford University. They have successfully used a generative adversarial model to for the super resolution of turbulence simulations. Again, super resolution is basically having a low resolution simulation, feeding it to a GAN, and producing a high resolution simulation. So that way you are saving a ton of computational expenditure. This is also the first time anybody has implemented super resolution on a three-dimensional simulation. And additionally, they have also made sure that the energy statistics of the flow field reconstruction of turbulence are also appropriately reconstructed and not simply the velocity vector fields. So this will have seminal consequences in the fluid mechanics community. Oh yeah, it's really tough doing it with 3D, and it's also just monumental in terms of the computational expenditure which it would be. And I always am unfairly biased towards fluids applications since that's my own field of research, but I try to include other fields as much as I can. So this is another interesting paper from Stanford Aerospace. So if any one of you is working on self-driving cars or automated or intelligent transport systems, this would be really relevant to you guys. In this paper, they try to use GANs for imitating driver behavior for developing self-driving cars. So this has, I think, like 200 citations or something, and this was developed by one of the grad students under this professor. He works a lot on using GANs for self-driving research. Also, this work came out in 2018 by Paganini et al. So for context, the motion of particle showers inside a calorimeter is extremely high dimensional, so it's really hard to simulate. And notably, it is also the most time consuming step in a simulation pipeline for Large Hadron Collider at CERN. So CERN has all these experiments where they are trying to bombard particles together and identify like how the atoms are being split. So they are also backed up by a lot of computational simulations, and notably the simulation of particles inside a calorimeter is the bottleneck which takes the most time. So these guys proposed a framework using GANs to accelerate these simulations. So okay, so now that you have a vague idea on what's happening, let's try to program like our own GAN and see how we can go ahead. Okay. You guys have the like the collab notebooks like loaded up, because I think it'll be really fun to go over this together, and I think that will be the most productive thing. Okay, can you guys see this? Oh yeah, no worries. This was a lot of fun, like going over the material and preparing things. I think like trying to come up with like material like makes things much more clear for me. So it's a win-win for both of us. Okay, so I sent like two notebooks, and the first one is basically for your reference. Um, can you see? Okay, so can you see this session titled Mega S3 dot IPN? Okay, so this Mega is session 3. This notebook essentially has the complete code to generate a GAN, and there are a few really advanced Python syntax that I have used for writing GANs, which I really didn't want to get into the session. Uh, but we can still go into the essence of building a GAN and look at how we can build a generator and a discriminator, and how we can build the loss functions and the training and all the essential parts. So the Mega S3 IPython notebook is basically for your reference, and the session, the version 2. So this essentially has a couple of, this is partially incomplete, and we'll go into it like now. So if everybody is ready, we can start going over the code. Would anyone want some more time to like set things up, or like open the notebook, or help with like setting up things in Collab? Okay, so it looks like most of you guys are ready. Okay, so all the sessions which we have been working on so far, we used Keras. Keras is a Python module to build neural networks. The popular alternative to using Keras is something called PyTorch. And PyTorch is more flexible when it comes to building things from scratch. So if you are a machine learning researcher, there's no way, I mean, it's hard to imagine me working with Keras, since Keras is more developed with an application based in mind. So if you want to develop your own loss functions and like write your own things, like make your own models, so PyTorch is more flexible. But on that note, I do want to mention that you can achieve the same result in Keras or PyTorch if you work hard enough. But I think it's just more convenient to simulate a GAN in PyTorch. So for this module, we'll be learning how to work with PyTorch. Okay, so let's make also the cool thing about Collab is you don't have to install anything. Everything comes pre-installed, and so this makes it really useful for demonstrations, since I think installing modules is a really hard task, uh, since it comes with like dependencies and like whatever. So okay, so we will be using NumPy, and we'll be using the NumPy is to manipulate data, PyTorch is to build neural networks, and PyTorch is just referred to as torch, and torch.nn as, so we'll import torch.nn as nn. So this is basically the neural network module associated with the PyTorch. And we have matplotlib and seaborn to plot things. So I'm importing clear output to plot dynamic plots in the IPython network. So if you enter, like if you do shift plus enter, it basically runs this cell. So this loading bar kind of says that the cell is being run, and once it stops, it means once it stops and gives you the number, it says it's done executing that line of cell. Okay, let's actually have this thing for reference to make sense of what we are doing and compare it with what we've been learning so far. So we have a random input and we have a generator. So the input to the generator is a random input, and we also have a discriminator. So there are a couple of things which we have to build. Okay, before we get into what we are building, I want to give a context on the problem which we are building like in this network. So so we've seen like in the beginning of our session, we've seen like all these images and faces which are being morphed. So these are like high dimensional data. So an image is like a two-dimensional image with like three channels for like the RGB values. So it's really complicated. But for this module, we'll only be looking at like the simplest case. We'll be looking into how we can use GANs to learn the normal distribution. Okay, so our real images is basically points which are taken from a normal distribution, and we want our generator to basically produce points which belong to normal distribution, and we want the discriminator to distinguish between the points generated from the real images and the generator. So for the random input, I'm trying to use the uniformly random distribution. So essentially the generator is taking in points from a uniform distribution, and it is trying to produce a normal distribution sample, so that they won't be discriminated, or they won't be able to be differentiated by the discriminator. And as always, the uh, we have the classification. Okay, so let's begin by writing the distributions. So I have a uniform distribution which I'll be using as an input to the generator, and we have the normal distribution which will be our input data set. So I just say torch.rand dot bs comma 1 is basically saying the standard deviation of the uniform distribution. So this varies from, I think it varies from 0 to 2, beginning at like centered at 1 or something. And I think, okay, and the get normal distribution, we essentially say like rand n, it means that it's a normal distribution, and we have a variance of 1, and we have a mean of 5. So this is our input data where the distribution is essentially with a mean of 5 and a variance of 1. And this is the input to the generator, which is uniform. And okay, also make sure to run these things like as we are going along. So okay, let's go back to the map. We have built the random input, and we have real images, or we have the data set. And if we have a data set, we can have a sample. So now we need to build the discriminator and the generator, and these are both neural networks. So let's build the neural networks for them. So here PyTorch is slightly more complicated to learn at the first glance, but it gives you like so much more flexibility when you're trying to learn. So so we write a generator class. I'll not be going into more in details on the syntax, but essentially we have a feed forward network where, similar to Keras, the key term for indicating that it is a neural network is basically nn.sequential. And now we can basically start start to write our network. So let's just begin with a linear layer, so and then in features is basically the input to the generator, and we know that we are working with a one-dimensional data. So the in features would be 1, and out features would be out features, we have more flexibility since we could have a hidden layer. And let's just say our hidden layer has 16 neurons. And now let's add some nonlinearity. And as we've seen in all the past sessions, uh, ReLU is the most common activation function. So let's just add that for nonlinearity. And finally, let's add our output layer. And so there's something which I want to mention. So since this is the input layer and this is the output layer, and they are both fully connected. So the number of out features from the first layer should match the number of in features in the second layer. So this has to be 16, and at the output, since we only have the probability of it being fake or real, so we only have one output. So that's it. We now have a generator network with one hidden layer. It takes in the inputs and it throws out an output. And similarly, let's write the code for a discriminator. So here, this is also very similar to what we wrote in the generator. We'll have like one input feature, and let's have the same number of hidden layers, same number of neurons in the hidden layer for comparison. And let's add the same nonlinearity. And okay, so this is basically the same, but the difference between both of them, this is the output of this model, this neural network model for the discriminator is essentially a probability. But so far, there are no restrictions to make this output value a probability. So in order to do that, we'll basically add a sigmoid function. So basically, a sigmoid function, the input to the sigmoid function can vary between -infinity to infinity, and it maps this range to 0 to 1. So if it starts getting like really broad and diverse values from the output, having a sigmoid makes sure that the output is a probability. Okay, so now we have a generator and we also have a discriminator. So let's run this thing, and now let's have the optimization parameters for both the generator and the discriminator. Since both of them have different loss values, it is um, ideal to have different optimization objects. I'm also saying that the learning rate is 0.10 power minus 3. This is also exactly what we did in the last example. Okay, so let's go back to our framework. So we have the discriminator network, we have the generator network, and we have a random input, and we can feed in the samples. So all that's left is to basically describe the loss functions for the generator and the discriminator and begin training and observe how our model is doing. So while updating, so let's begin by writing the module to update the discriminator. So we know that the real samples are basically the normal distribution, and that takes in the batch size. Now, the probability that real is real, or probability that something real is identified as real by the discriminator, is basically, so we have written the discriminator as disk, and we know that the output of a discriminator is basically the probability that something is real. So we just write disk of real samples. And And we know that the noise is a uniform distribution. And the generator samples can be obtained by just saying gen of noise. So this is the G of Z term, and probability that fake or the generator samples is fake is basically 1 minus discriminator of generator sample. So this is 1 minus d of G of Z, and this is d of x. Okay, so now that we know the probabilities, let's write the loss function. So we know that the loss function for a discriminator has two values. One is the log of the probability that something real is real, and then we also have the other term which says which is saying fake is fake. So, and we also have the expectation value in front of our loss function. So we just write mean. Okay, so the loss function of the discriminator is essentially maximizing the probability that something real is real and something fake is fake. That's it. And these three lines basically take our loss function. They try to generate the gradients with respect to the weights and start updating the weights. This return function is only for analyzing things and doesn't really have any consequence since this step already updates the weights. And okay, now let's try to let's try to see how we can update the generator. So we know that the noise is basically uniform, and we have BS, and generator samples are generated noise, and probability something fake is real is basically discriminator of. Okay, so this is G of Z, and this is G of this is D of G of Z. And let's write the loss function for a generator. So this is trying to maximize dot log of probability fake is real. And then we take the mean for the expected value. So again, these three steps are to update. So we have a generator loss and we also have a discriminator loss. And we have these modules which basically update the generator and the discriminators. So, okay. So now we know we have the modules to update the generator and we have a module to update the discriminator. Let's go back to our blueprint. So now literally everything is in place and all we have to do is basically train the model. So as we have seen, as we have looked like before, training a discriminator should be given like more weightage. So if we are training the GAN on like 100 epochs, we are essentially saying, so I have chosen an arbitrary parameter. I have chosen n ops is equal to 50. So it's basically saying in each of the 100 epochs, update my discriminator like 50 times and update my generator only once. And so this is what we've been talking about like previously, where I said we need to give more weightage to updating the generator than the discriminator. I think I just said it in the I just said it in reverse. So we need more weightage for the discriminator and lesser weightage for the generator. So This shows a number, so it has already ran. Now let's try to see the plots. So this code is basically like really fancy to see what's happening. So okay, let's try to understand the different things which I have plotted. So there are three lines in this plot. The first one is the fake distribution, which are generator generated. So this is seen in blue. This still looks like a uniform distribution. It's not at all close to the real distribution. So the real distribution is a normal distribution, which is centered around 5 with a variance of 1. So we know that the real distribution is what we have in mind, but the generator is still not close. Also, I'm also plotting the P of real values, which are outputted from the discriminator. As we can see, they are like pretty low for the generator. So at this point in training, like after training for 100 epochs, we know that the the discriminator is easily able to identify that something fake is fake. So in order to get better at learning the normal distribution, let's just keep going for more like a larger number of epochs. Also at the same time, it's actually really cool to look at the distributions being updated like online. So this is why I have imported the Seaborn module, and I also have the clear output function, which I have like in the first lines of importing things. So right now I'm basically saying I have 10,000 epochs and I'm updating things, and I'm plotting things, and I'm also dynamically plotting things for every 100 epochs. So let's see what the output should be. Okay, so each update for shows how the models are learning after 100 epochs. So we can see that the distribution is closely becoming like the normal distribution. So this is a real distribution and this is a fake distribution. So the blue distribution is trying to become more and more alike. So after maybe like 10,000 or 100,000 epochs, it'll essentially be indistinguishable between the normal distribution and the fake distribution that we have. I think while it's running, it'll be interesting to look at the game theoretic approach of these two models. So we have two agents in this game which are fighting against one another. We have a generator and a discriminator. So if we try to understand the Nash equilibrium for this game, it would basically be something like the generator would produce samples which are so good and so indistinguishable from the actual data that the discriminator would essentially output probabilities which would be zero point 0.5 for both the real data and also the fake data. So the Nash equilibrium for the discriminator would be just 0 0.5. So it would be so if we are looking at the P real value, which is seen in green, we want this line to be as close to 0 0.5 as possible, since that is the Nash equilibrium for this problem. As we can see, it is more and more becoming close to 0 0.5, which means the discriminator is essentially not able to distinguish that something is real or fake. And our generator is just getting really good at fooling the discriminator. So it's starting to look really close, but if you look at it, it's doing a really bad job at the edges. So so we have this line which is mostly 0 0.5, but it's still slightly bad towards this edge, and apparently this is doing better on this side. So you get the whole idea. So in this example, let's just keep this running, and that will be the end of the session mostly. So we have seen how we can learn a one-dimensional data using a GAN. So if we update this to a complicated data set, we can start training images. So instead of simple random points or random samples, if you start feeding in like fluid simulations of, say, non-time resolved data or non-time resolved PIV data or non-time resolved simulations, and if you feed them into a GAN, you can essentially produce time resolved simulations, which would have been like monumentally complicated to simulate if you are doing them in a time resolved sense. So GANs are really useful for simulating all kinds of dynamical systems. So this was a 1D example, but it just gets so much more complicated for doing 2D examples or fluid simulations, but you essentially have the idea behind what you can do. Okay, so do you guys have any questions regarding any of the code or any of the material which we have covered so far?